All right, today we are tackling a really fascinating engineering puzzle. We're going to build a machine that can make decisions, remember things, and carry out actions in a very specific order. But here's the real kicker. We're doing it all without a single line of code. No microchips, no electricity. Nope. We're going to build a brain that runs entirely on compressed air. So, let's dive right in.
So that's really the big question, isn't it? How do you create logic and memory and control without any electronics? Well, the answer is something called pneumatics. It's the science of using pressurized gas, air, to get work done. It's all about channeling that flow of air in a really clever way. By using a series of special switches and valves, you can actually create intelligent, automated actions. This is the heart of mechanical logic, and it is just brilliant.
And here is our exact challenge, straight from Experiment 7.0. Now, I know it sounds a little dense, but let's just break it down. We need a piston to push out when we press one button. Okay, simple enough. But then it has to stay out, even after we let go of the button. Then, to bring it back, we have to press a second button. But here's the catch. It will only come back if that first button has been released. Wow. That is a whole lot of rules for a system with no computer.
To solve a puzzle like this one, first you gotta know your tools. And in our case, the toolkit is made up of these pneumatic components. These are the fundamental building blocks we're going to use to construct our little air-powered logic circuit.
So, first up, we've got the muscle of the whole operation, the double-acting cylinder, or DAC for short. Just think of it like a mechanical arm. You see, unlike a simple cylinder that can only push one way, a DAC has two ports for air. We can send compressed air into one port to push the piston out, and then send it into the other port to pull it right back in. This gives us really precise control over both extending and retracting.
Next, we need a way to actually talk to our system, right? And that's the job of this guy, the 3-2-way push-button valve. It's basically our main input, a simple switch. When you press the button down, it reroutes the air, sending out a signal. Let go, and a spring pushes it right back. This is exactly how we're going to tell our circuit to start and stop. And this diagram just shows that basic relationship perfectly. What we're seeing here are two very simple circuits. In both of them, a valve at the bottom acts as the switch. It's directing the air from the source to the cylinder up top, which is our muscle. By controlling the switch, we control the muscle. This is the fundamental idea that we're going to build everything on.
Okay, so we've got our components. Now for the really clever part, arranging them in just the right way so that they're forced to follow the strict rules of our puzzle. This isn't just about connecting tubes, it's about designing an intelligent pathway for the air to follow.
So here are those rules from Experiment 7.0, but broken down into simple if-then logic. First, if we press button A, the cylinder extends. Check. Second, it has to stay extended, even after we let go. That's basically a memory function, right? And third, to make it retract, two things have to happen. Button B is pressed and button A is released. That "and" right there, that is the crucial part that makes this whole puzzle so interesting. So, how do we actually build these rules into a physical circuit? Well, we use special components that act just like the logic gates inside a computer chip. But they don't use electricity, they use air pressure. And the two most important ones for us today are the OR valve and the AND valve. These things are the real brains of the operation.
Now take a look at this. This diagram shows us OR logic in action. See that component in the middle with the little ball inside? That's a shuttle valve. Air can come in from the left, from valve 1.2, or it can come in from the right, from valve 1.4. Either way, that little ball just slides over to block the other path, and the air flows straight out the top. This is perfect for when you need something to happen from one of several different inputs.
And here is its counterpart, AND logic. This component is called a twin pressure valve. Now this one will only let air pass through to the outlet if, and only if, it gets pressure from both inputs at the exact same time. If just one button is pressed, nope, the air is blocked. This is exactly what we need for that tricky retraction rule in our puzzle.
Okay, we have the muscle, we have the switches, and we have the logic gates. We understand the rules of the puzzle. It is time to put it all together. Let's assemble the full pneumatic circuit that solves Experiment 7.0.
But before we look at the final diagram, here's how you'd actually do this in the real world. It's surprisingly straightforward. You just mount the components on a board, you set your air pressure, usually around 6 bar is good, and then you connect all the little plastic tubes just like the diagram says. Then you turn on the air and see if your air-powered brain does what it's supposed to do.
And here it is, the complete solution.
Let's walk through this. To get this cylinder to extend, we press one of these two buttons. That signal flows into our OR gate, the shuttle valve we talked about. This flips the main valve, which acts as the system's memory. Air gets pushed into the cylinder, it extends, and then it holds that position even after we let go. Now for the tricky part, retracting it. To pull the cylinder back, two things have to happen. We need a signal from this other button, and we need a signal that confirms the first button is released. Those two signals meet at our AND gate, the twin pressure valve. Only when both are present does it send air to flip the memory valve back and the cylinder retracts. Every single rule from our puzzle is solved, all with just the flow of air.
So we did it. We solved the puzzle. And it's a really satisfying piece of engineering. But you know, this isn't just some classroom exercise. This kind of computer-free automation is actually incredibly important, and it's used all over the place in the real world. Let's see how this all leads to some very practical applications.
Pneumatic logic is really the workhorse of so many industries. Think about a factory assembly line. You might use a circuit just like this to clamp a part in place while a robot works on it. Or maybe for pressing something into a mold with the exact same force every single time. Really, any repetitive industrial task that needs a simple, robust, and super reliable sequence of actions is a perfect job for pneumatic automation. It's cheap, it's powerful, and it's incredibly durable. So the main takeaway here is that by cleverly rounding something as simple as air, we can create these surprisingly complex and useful behaviors. It really makes you wonder, doesn't it? Without any electronics at all, just using these basic building blocks of logic, what's the most sophisticated machine you could design? What's the most complex task you could automate using nothing but air?
Please like, share, and subscribe for more learning and appreciation. And smash! I am Batman.